In this video, we'll talk through the intramolecular forces topic from Higher Chemistry Unit 1. By the end of this video, you should be able to explain the effect of electronegativity on the electrons in a covalent bond, be able to assign partial charges to show a dipole within a bond, and also the relationship between the differences in electronegativity and the type of bonding that's present. Bonding that we find inside of molecules is termed intramolecular, and the bonding between molecules is intermolecular. The intramolecular bonding types have different properties, but they're arranged into a continuum of a sliding scale where we have non-polar covalent on one extreme and ionic bonding at the other extreme. From previous work in chemistry, you should be aware that a covalent bond is where we have our positive nuclei being held together by their attraction for the shared pair of electrons, where we have positives and negatives attracting. Whether we have non-polar or pure covalent versus polar covalent bonds depends on the electronegativity. And we are going to imagine it as a tug of war with the pull on the electrons. If we have a non-polar bond, this means that the atoms will have the same electronegativity or the same pull on those shared pair of electrons. If this is the case, we have a non-polar bond where we have the electrons being shared equally. If you've got atoms with different electronegativities, they will form a polar covalent bond, and these electrons will be shared unequally. This means that the electrons will be closer to one side than the other. Examples of how to do this: we find our chemicals and we look up our electronegativities, we calculate the difference, and we can then term this bond as being polar because there is a difference in electronegativity. If we have phosphorus and hydrogen, they have equal values of electronegativity. Therefore, there's no difference, so we have a non-polar bond here. And with oxygen and hydrogen, we have a difference of 1.2, which makes this a polar bond. The oxygen to hydrogen bond will be more polar than the other two shown. If you're looking at older questions, they'll have different values of electronegativity because they will use an older version of the data booklet. Chlorine, for example, was 3.0, which means sometimes when you're answering questions, the values don't quite match up. What the questions will ask you, though, will be which of these will be the most polar or the most non-polar, the least polar or the least non-polar. So we are looking for the biggest difference or the smallest difference depending on the question. Next, let's look at dipoles. And in a dipole, you're going to have one element which is going to become slightly negative and one that's going to become slightly positive. If we look at the electronegativities, we can look at the difference between the two. The one with the higher value will become slightly negative. So bromine will be slightly negative in this one. And if we compare chlorine and hydrogen, chlorine has a higher value, so chlorine would become slightly negative. This question wants us to find which of these has the most polar bonds. We're looking for the largest difference in electronegativity. Find the values of each of them. We look at our differences, and our cesium to chlorine bond has the highest electronegativity difference, therefore it will be our most polar bond. In this question, we're talking about nitrogen bonding to element X, forming a bond where the electrons are shared equally. This means we're looking for a non-polar bond, and that means we're looking for something that has the same electronegativity as nitrogen, and nitrogen's value is 3.0. We find our values for each of these from the data booklet, and we see that bromine has got the same value, therefore it would make a non-polar bond with nitrogen. In this question, we're asked about our dipole, and we're talking about chlorine. We are therefore looking for an element that has a higher electronegativity than chlorine. Chlorine has a value of 3.2. Here are the values for the other chemicals. Therefore, fluorine would become slightly negative because it's got a higher electronegativity than chlorine. Now let's look at the extreme version of ionic bonding, where one atom's electronegativity is so much greater than the other that instead of sharing the electrons, it takes the electron from the other atom. An example would be found in lithium fluoride, where we have a difference of 3 between the two. Because fluorine has a higher value, it's going to gain an electron from the lithium, and this forms our positive and negative ions. These are attracted to each other, and this is called an ionic bond. When you're given an ionic formula, it's usually written as the simplest ratio of each ion. So despite it forming an ionic lattice, because the ratio of lithium to fluorine is 1:1, it will be written as LiF. This doesn't mean there's only 2 ions involved. There would be lots and lots of ions. It's just the ratio we look at for this formula. In our bonding continuum, we're going to link our types of bonding to the differences in electronegativity. And by calculating the differences in electronegativity, we can predict which type of bonding is going to be present. We can then back that up looking at properties, but as an initial starting point, this is a good way of predicting which type of bonding will be present. This question, we're going to be asked to explain the polarities of these 2 molecules. They have the same shape, so we're not going to worry about our intermolecular forces. We're only going to worry for this question about the differences in electronegativity. We look at the values for nitrogen and hydrogen, and then nitrogen and chlorine. From these values, we can see that ammonia has a larger difference in electronegativity. Therefore, ammonia will be our polar molecule, and our trichloramine will be our more non-polar molecule. Hopefully by the end of this video, you'll be able to explain the effect of electronegativity on the electrons in a bond, being able to draw in dipoles showing the charges on atoms in a bond, and also being able to explain the relationship between the differences in electronegativity and the type of bonding, be that non-polar, polar, or ionic. Thank you for watching. Goodbye.